Hello, my name is Fabian, and I'm going to talk about the YAGO knowledge base. So, if you're in this session, you know what a knowledge base is. Yeah. So you've spent already like 2 hours talking about knowledge bases, knowledge graphs, knowledge bases. So there are lots of applications of knowledge bases, and they're particularly popular here at SIGIR. And I want to add some more applications to the ones we've already seen this morning. So a huge fraction of searches on the web is actually about named entities. So for example, if you search Elvis Presley on Google or also on Bing, yeah, what you get is directly a knowledge card. So you get directly information about this particular entity, like where he was born and when he was born and so on. Yeah, and this is fed by a knowledge graph that Google and Bing are building. And actually 50% of Google searches end with the user just watching this knowledge card and then moving away. Yeah, they don't even click on a link. So knowledge bases do have their role to play in search. Other applications are queries that ask for entities by properties. So for example, if you ask a singer who was born on January 8th, 1935, then Google can answer this query right away without going to any knowledge, to any web page, actually just from their knowledge graph. That is it's actually Elvis who was born on that particular date. Yeah? And they can even have more complex queries if you ask who's the mayor of the city where Elvis Presley was born. That's pretty cool, and Google can actually answer this query with joint reasoning from their knowledge graph. So, and finally, knowledge graphs also help with auto-completion. So if you search Elvis P, then Google will auto-complete this with Elvis Presley, the person, or Elvis Presley, the movie. So knowledge graphs have their role to play. Now, which knowledge graph do we choose? So there are actually lots of them that are available online. So BabelNet, WordNet, ConceptNet, DBpedia, as we've just seen in the previous talk, or Wikidata. And interestingly, so most of them either have no schema and no taxonomy, or they have very few instances. So DBpedia, for example, has in its clean part just is still a lot, but for today's standards a few, just 4 million instances. So that's pretty small actually. And Wikidata, which is very large, has lots of instances, actually is not very strong on the schema and taxonomy. So why is that? Wikidata is a collaborative project where 20,000 volunteers collaborate to build a knowledge graph. It's a fantastic project. And these 20,000 volunteers can very well agree where Elvis Presley was born. But if they want to agree on the taxonomy and the schema, it's much harder. So as an example, take the city of Paris in France. If you look at the taxonomy of Paris, you will see there are 60 classes for the city of Paris, and they're actually in a loop, so they contain loops. And Paris is actually in the category of mathematical objects. Why is that? Because somebody decided that Paris is a geographical location, which is a spatial object, and spatial objects are mathematical objects. Yeah, so this gives this kind of structure. So how can we deal with this? Here is our proposal of what to do. We use a trick, and the trick is that we manually control the top level schema and the top level of the taxonomy. Yeah? And this is how we make sure it's actually clean at the top level. And the bottom level, like the facts, we import from Wikidata, and this is where we get the richness and the size from. Yeah? So let's look into this in more detail. So the top level actually, the top level classes, we take them from schema.org. And schema.org is a collaboration of major search engines like Google, Microsoft, Yandex, and Yahoo, and so on. And they have defined the taxonomy. Yeah, that's pretty clean. And we use and adapt these for our purposes. The same goes for the constraints. So we manually define constraints in Shackle to define every single property and every single class and say what properties these classes can have. Here, for example, we use the GTINs for commercial products, and we say that GTINs have to be strings, they have to follow this format. Every commercial product can have at most one GTIN and so on. Yeah? The facts come from Wikidata, but we make them with legible names and relations from schema.org. And the lower level classes also come from Wikidata, but we clean them up, we remove the loops. So how do we know that what we're doing is good? Well, there are a number of intrinsic measures that we use. So we have no cycles, we have legible entity names, we have a small number of paths to the root and so on. And we can also show that by using YAGO, we can disambiguate facts more easily. If you say, I love the city of light, Paris, it can be Paris in France and Texas, Paris Hilton. If you augment this data with the data from the YAGO knowledge base, then you can actually disambiguate, figure out that this must be Paris. So this is the YAGO knowledge base. It is a large and clean knowledge base that is a principal combination of schema.org and Wikidata. It has 130,000 classes, 50 million entities. Compare this to the 4 million we saw before. 150 million facts. It's provably consistent. You can actually run this on an old verifier and a shackled verifier. You can prove it's logically consistent. Has legible entity names, legible taxonomy, and is used by DBpedia and IBM Watson. If you want to know more, please check out our webpage or come see my poster tomorrow. Thank you for your attention.
Okay, thanks very much for a nice presentation. So yeah.